Hello, everyone. Welcome to the webinar hosted by SNIA Ethernet Storage Forum. Today's topic is getting from here to there part Sepia about series, everything you wanted to know about storage but were too proud to ask. Today we have three speakers. Chad Hinz. Chad is a principal engineer for the Cisco Commercial East area, focusing on designing enterprise solutions for customers around the Cisco data center technology. We have John Kim. John is the Director of Storage Marketing at Mellanox Technologies, and where he helps storage customers and vendors benefit from high-performance networking. John is also the chair of the SNIA Ethernet Storage Forum. We also have Alex McDonough. Alex has more than 30 years experience in a variety of roles with some of the best-known names in the software industry. Alex right now is part of NetApp's CTO office, supporting industry activities and also promotes technology and standard-based solutions. Alex is the chair of SNIA CSI Cloud Storage Initiative, vice chair of SNIA ESF, and also co-chair of SNIA SSSI Solid State Storage Initiative. I'm Fred Zhang. I'm the moderator of today's webinar. I'm the Ethernet Controller Product Line Manager in Intel. Before we move on to the topic, I want to have a quick introduction of SNIA. SNIA is the Storage Network Industry Association. It's a nonprofit trade association dedicating for leading the storage industry worldwide. It develops and promotes standards, technology, and education services. Right now, SNIA is made of 160 unique member companies and also has 3,500 active contributing members that can reach a community of over 50,000 IT end users and storage professionals worldwide. You can learn more information at snia.org/technical. Before we get started, I want everyone to take a look at the legal notice. We'll post the presentation and a webinar at the SNIA ESF website after the presentation. And also, please feel free to use the content as long as you cite SNIA as the source, and please keep the entirety of the content. As highlighted on the bottom, use the content at your own risk. During the presentation, also you can submit your questions. We might not be able to answer all the questions, but we will capture all the questions and we'll have a Q&A blog after the session, and we'll post the blog on the website. So today we have three items on the agenda. We'll talk about encapsulating versus tunneling, IOPS versus latency versus jitter, and also QoS. From here, I want to hand my mic to Chad. Chad, please take over for the first topic.
Thanks, Fred, and thanks everybody for joining. So I am going to hit the first topic, which is encapsulation versus tunneling. So we wanted to hit on this topic for you guys because we feel like from getting here to there, a lot of what happens in forwarding, either coming out of a storage unit, out of a server, or through networking equipment, there's a lot of confusion between these two terms. In a lot of cases, people think they're the same thing. And so what we're going to do is we're going to kind of visit what the definitions are for encapsulation and tunneling, and then we're going to get a little bit deeper and show you exactly the difference between the two and then how they're complementary to each other as well. So to start off, I'm going to pause for a second, and I'm going to let you read what's on the screen for the definitions of encapsulation and tunneling. But from a high level, what you'll see is as you're reading through these, that there's very similar terms in each one of them. In a lot of cases, people always confuse what encapsulation is versus tunneling, and sometimes are intermingling what the actual definitions are. So I'll pause for a second, like I said I would, and let you read that for a second. So after you finish that, it explains it, right? You should be good to go. We don't need to talk about encapsulation versus tunneling. And this is really the crux of why we want to talk about this today. Is it's really about as clear as mud. A lot of cases, the definitions that you'll see that if you search on Google or any of your favorite search engine, if you go and look at definitions from different vendors, is that a lot of people are mixing a lot of the definitions together. So what we're going to go is we're going to go a little bit deeper. We're going to first hit on encapsulation so you get an understanding of what an encapsulation is. We're going to do it at a real basic level. We're going to reference the OSI model. And then we're going to get into what tunneling is, and then how do they complement each other. So let's just get into it. So a deeper dive into the encapsulation. Really if we're looking at the OSI model that we have on the left-hand side, when we look at encapsulation, anytime I take an original frame and do not modify it and put some type of header on it, I am encapsulating that original frame. As you can see here, from going from layer 7 down to layer 1, as I go to the different layers of the OSI model, I'm adding multiple different headers, which is adding encapsulation to the packet, okay, to the original frame. When I get to an end state where the device is actually gathering that information and now has to go and read the original frame, another process happens, which is de-encapsulation. And what de-encapsulation does is it's taking the headers off in the reverse order that we're showing here. So if I started at layer 7 and went down to layer 1, I'm adding my headers. As I receive that full entire packet with all the encapsulation in it, I then decapsulate it by taking off the headers to ultimately get to my original frame so I can process it. So in summary, what I'm doing with encapsulation is that I'm taking the original data unit unchanged and then wrapping it or encapsulating it into another frame by using headers on top of it. Hopefully that clears up what encapsulation in its basic form is. Now this encapsulation could be from a networking device, such as a router. We're going to actually reference routers in this case. But it could be from a storage unit that's going from one storage unit to another storage unit, and it's trying to encapsulate, and we'll talk about how it tunnels from there next. It could be from a switch. It could be from multiple different types of devices. So let's get into tunneling. Essentially what tunneling is when you encapsulate, that device that encapsulates is considered a tunnel endpoint. Okay, so in the case that we have up here in the deeper dive, the logical view we have is we have A and B. A is trying to send to F. Okay, so A has an original frame that has come into it, and it needs to communicate with something that is hanging off of F. So what happens is that A sends to B, B then encapsulates and tunnels over the original network, over the original protocol to E. E decapsulates it and then sends it on to F so that they can decapsulate again to get to the proper frame. So the real key here is in a physical view, the routers that might live or devices that might live in between B and E, they don't see anything but the encapsulated header. They don't see the original frame. They don't see anything. So really what they're focused on is forwarding based on what the outside header has, which is the encapsulated part. So really all tunneling is taking a packet, encapsulating it, sending it over another protocol to another side, decapsulating it, and sending it on. It's that whole process of encapsulation, transmission, decapsulation. Okay, so you can see that why people sometimes get confused between just doing the process of encapsulation versus doing the full transmission plus the decapsulation, which is what we consider tunneling. So let's get a little bit deeper into that. Let's give you an example. So putting them all together and how they complement each other is that in this scenario, the logical view that we just showed, we have A, which has IP version 6 endpoints on it that wants to send something to F, just the same scenario we just talked about. And in between B and E, where we have our tunnel, we actually only have a network that supports IP version 4. So what we're doing here is that when A wants to transmit an IPv6 base packet or to a destination of another IPv6, but in between the protocol that they're trying to do doesn't support it. So for instance, IPv6 trying to talk to IPv6, C and D don't support IPv6, they're IPv4 only. So in this case, what happens is that B and E are what we call a dual stack router. And this doesn't have to be routers like we talked about. It could be any device that supports dual stacking. And it will have IPv6 and IPv4 support. So when the original frame comes in from a source of IPv6 to a destination of IPv6, and B realizes, I cannot put this on this link that's going to C because it's only IPv4, what he'll do is he'll encapsulate it. He'll encapsulate the original frame and put an IPv4 header on it, sourcing it from his outside IP address, which is IPv4, destined to E's IPv4 outside address. And what C and D only see is the IPv4 encapsulation. So essentially, he's building an IPv6 over an IPv4 tunnel. When the packet is received on E, he realizes that inside, he decapsulates it, realizes that it's an IPv6 packet, and then sends it on to F. So in summary, tunneling is, and I am going to read from the slide, which I don't like to do usually, but tunneling is the method used to transfer a payload of one protocol over another protocol. And it's the process of encapsulation, the frame using the header, so it can be tunneled. Then it's putting it through the tunnel, then the transmission of it, and decapsulating it on the other side. That whole thing is called tunneling. Encapsulation is just one part of that process, just like decapsulation is a part of that process. So we have tunnel endpoints. The tunnel endpoints, they're the ones that are doing the encap and the decap, and then they're sending that over that tunnel. Now there's many different tunneling protocols that are out there. There's GRE, there is IPv6, there's IPv6 tunneling over IPv4, there's Lisp, there's a locator ID separation protocol, MPLS is a version of tunneling. So there's a lot of different methods to do this, but when you get down to the basics, what happens is you have tunnel endpoints that encap, decap, and then send them over a logical tunnel that goes over top of another media or another protocol. So with that, I'll hand it back to Fred for any questions, or we can move on to the next section. That goes over the tunneling and encapsulation. Hopefully that clears that up for you.
Okay. Thank you, Chad. Next topic, we'll talk about IOPS versus latency versus jitter. So hand the mic over to John. John, please take over from here.
Thank you, Fred. Hello, everyone. This is John Kim. I'm going to cover IOPS versus latency versus jitter. So let's go ahead and get started. And if there are any questions, go ahead and send your questions in with the online question tool, and Fred will insert the questions wherever appropriate. So first, let's define IOPS. IOPS stands for Input-Output Operations Per Second, and it's pronounced IOPS. And essentially, each IOP is a storage transaction that's been completed. IOPS can be read or write or both, and they can be block or file. So, for example, you could have an IOPS workload that's 100% read, or 50% read, 50% write, or 100% write, or anywhere in between. And again, it can be done on a block or file storage. It's almost never done on object storage. There are different ways to measure different workloads. IOPS is usually how you measure small transactions, especially random storage transactions, where if you're measuring large or sequential transactions or large sequential workloads, usually you use throughput or bandwidth or megabytes per second, which is a way of measuring throughput and bandwidth. Who would want lots of IOPS? What kinds of workloads want that? So it's usually a random workload, and it's usually with small transactions. It's more frequently block, as I mentioned, could be files, so small blocks or small files. Types of applications that need this, often databases, especially an OLTP database workload. Not all database workloads are IOPS. Some database workloads are actually more throughput or large sequential, but most database workloads, especially the OLTP query type workloads, have lots of small transactions, so you measure them in IOPS. Similar with virtual machines, most of the time you have virtual machines, and while each virtual machine might have a sequential workload or not, when you combine all those virtual machine workloads together through a hypervisor, you get something called the IO blender effect. And effectively, you get a small random workload, even if when you combine the workloads of all the different machines going through the hypervisor, the virtual machines. There are also some technical computing apps that require IOPS, but again, it varies. Some of those applications want lots of throughput or lots of bandwidth, and some of them want lots of IOPS, depending on, again, whether they tend to have large or small transactions. What affects IOPS? So the first aspect is the performance of the media that's being used in the storage. It could be hard drives, SSDs, DRAM, RAM disk, if it's an in-memory application. But the key is that the storage device, or each storage device and the storage devices combined, have some kind of limit of how many IOPS they can support. And that number could be different between read and write IOPS. The second thing affecting IOPS is the latency of the data path. So if you look at the path from the client or from the application server to the network, to the storage controller, down to the media, and all the way back to the application server or to the client, you have to add up all the latency of the different stages in between. And the greater the latency, the lower the number of IOPS you can support, or the lower the latency, the more IOPS you can support. And therefore, if you want to increase the number of IOPS, one way is to reduce the latency. And this can be done through more efficient software or through caching or RDMA. Another way is to increase the IOPS capability of the different components of your solution. That could be the storage controller, it could be the network, it could be the media, the storage media involved. So again, if you increase whatever you find out whichever part is the bottleneck or is limiting the IOPS capability, and you increase that, and then typically you'll find that some other part of the solution stack has become the bottleneck, and then you can increase that. Another way to increase IOPS is in some workloads, you can increase the parallelism. That means that you have more threads or more jobs so that the servers or the storage device are handling more queues and more tasks simultaneously, and this usually lets them run at closer to maximum capacity and therefore get more IOPS. Not always, but in many cases you'll find that higher parallelism allows you to do more IOPS. Now let's look at latency. I mentioned that latency can affect IOPS. Higher latency is bad, lower latency is better in terms of trying to get more IOPS. Latency is the time to complete one storage transaction. In some cases, it's the time to start the transaction, but usually it's the time to complete it. It's like the reaction time for storage. As I mentioned, lower latency gives you higher IOPS. And there are a couple ways to measure latency. The two most common ways are to look at average latency. So I simply take the total number of transactions divided by the time it took to finish the transactions, and that's my average latency. Or I may look at the 99.9, x99 something latency, and that's sort of looking at the long tail latency, and that's saying how many of my transactions were under some latency limit, and I'll talk more about that later. Who needs low latency? Well, it's actually often the same workloads that need high IOPS. So database, virtual machines, technical computing. If you're doing something like high frequency trading, then low latency can matter. If you're doing real-time analysis of web traffic or something, web ads or any sort of real-time analysis, then you might need like a self-driving car, then you might need low latency, because higher latency may mean you don't make the right decision in time. Again, it's usually small random workloads. And latency usually does not have much effect on large or sequential I/O. And the reason is when I have a very large transaction, let's say I'm moving 1 megabyte at a time, or even half a megabyte, or 4 megabytes of data at a time. If it takes me a few extra microseconds or milliseconds to start each transaction, the user or application is probably not going to notice by the time I get to the end of moving the 1 megabyte or 4 megabytes. Where if I'm moving 1 kilobyte or 4 kilobytes at a time, or if I were in voice over IP traffic, it could be really small, even smaller packets, then the latency of each packet can have a big effect on the overall performance. What affects latency? So not surprisingly, the latency of the I/O path. So again, we look at from the client through the network, through the software, the storage controller, the media, and all the way back. And you can lower that latency by reducing the latency at different stages in the process. Latency is usually the combined latency of all the stages. So reducing latency anywhere along the line can usually cut the total latency. A good way on the storage side is better software or smarter software that's better at, is more efficient or more better at handling, figuring out which media is going to serve the requests. Caching can help at different layers, certainly, by responding faster, effectively making the media look faster, or by getting the reaction time closer to the requester or closer to the client by caching the data that you wanted most of the time close to the person who needs it. And RDMA, again, is a way to reduce number of software copies or do direct memory transfers and can lower latency in some cases. Is there a trade-off between latency and IOPS? So most of the time, reducing latency also increases IOPS, and so you get the same benefit. However, I mentioned earlier, parallelism, or running more jobs or more queues simultaneously, is something which can increase IOPS, but sometimes also increases latency. And the reason is that you have more tasks going at the same time, and so the different CPUs or different controllers, while they're getting more done, they may have to switch back and forth between different job queues or different streams, and therefore get higher latency for them, even as they're getting more total IOPS done. So related to latency is jitter. So let's define it. First, jitter is the variation or unpredictability in latency. It sort of says that, I don't know, I cannot guarantee, or I'm not sure exactly what kind of latency I'm going to get on each transaction. And I didn't mention this, but latency can often be classified as deterministic or non-deterministic. And deterministic usually means that I know for sure that latency will not exceed some number, or all latency will be below some certain target. And non-deterministic latency means I cannot be sure of that even though the average latency may be knowable or below, fairly low, occasionally I could get a particular transaction that has unusually high latency. And this is sometimes called the long tail, because latency distributions, as we'll see in the next slide, often have a statistical distribution with a long tail off to the right, meaning there are a small number of transactions that just have unusually high latency, even though most of the transactions have a short average latency. So jitter is that variability. Jitter can be static or transient. Static would mean that I pretty consistently have these outliers or these long tail incidents of high latency and that are coming all the time. And transient would be that something unusual happens and gives me a sudden burst of high or unpredictable latency, and then when the incident is resolved, then the jitter goes away and the latency returns back to its normal distribution, where I don't have these unusual or sort of random incidents of high latency. Jitter is undesirable in storage and in networking because it makes performance unpredictable. It says that most of the time the latency is low or on target where I expect, but every once in a while, and I don't know when, the latency is just going to be higher than expected. And for certain workloads like audio or streaming voice or streaming video, voice over IP, certain kinds of analytical transactions, this unexpected latency, this jitter, can be very disruptive. It can cause session to get dropped or connection to get dropped, or people to have a bad experience with their online. So some apps just cannot handle jitter and some can. So I mentioned this long tail latency, or the 99.xx percentile measurement, and this is a graphical example of that. So here, the blue line shows a distribution of latency. So if I took all my transactions and I plotted the latency, which is measured on the bottom, and it could be milliseconds, or in this case it's milliseconds, but it could be microseconds or nanoseconds. And then I show how often it happens, and I get this curve. And in a regular statistical distribution curve, it would be a curve that's symmetrical on both sides. But this is a long tail curve, which is common in latency, and it says that most of my transactions, my median latency, or the most frequent latency is, in this case, 4 milliseconds. My average or mean latency is about 5 or 5 and a little over 5 milliseconds. But there's this long tail off to the right of these occasional unexpected cases where the latency is just very high. So one way to measure that is to say, what's my 99th percentile latency? In this case, about 99% of, I said it's 12 milliseconds. So 99% of the transactions finish in 12 milliseconds or less. But that might not be good enough. I might need to know that's 1 in 100 transactions is more than 12 milliseconds. I may need to say, what is my 99.9th percentile latency? In this case, it's 16.5 milliseconds. So 1 out of 1,000 transactions has latency higher than 16.5 milliseconds. And if you're very sensitive, you might even plot the 99.99th percentile latency, which I didn't draw here, which would say that 1 in 10,000 transactions it exceeds my target. So this is a way to measure jitter. And the higher the number under the 99 point whatever XX percentile latency is, shows the worse the jitter or the more jitter I have. What affects jitter? So it's basically things that cause a pause or a contention or a context switch somewhere in this whole storage in the storage stack, and therefore causes the latency to suddenly increase for a few transactions. So in the storage controller, it could be a checkpoint, a snapshot, replication, or any other kind of housekeeping task that the storage controller has to do. It's anything that can make the CPU too busy or force a context switch, or maybe the CPU suddenly has to go to a different side if you have two CPUs to a network card or storage media that's connected on the other side, and with NUMA affinity. So these are all things which can cause jitter, or basically variation in the latency on the controller. On the media, it could be if it's a hard drive, a thermal recalibration, or some kind of other process or attempt to recover a write or recover a read on the drive. With flash drives, with SSDs, it could be write coalescing, it could be garbage collection, wear leveling, and generally for the storage, anything that has a failed device or has a RAID rebuild or anything that's cleaning up or doing correction or error checking can cause this high jitter, because it suddenly goes out there and says, hey, before I give you the data you wanted, I have to go do this cleanup or this housekeeping work. On the network, latency is mostly caused by congestion or packet loss or a change in path. So an advantage of multipath networking is redundancy, but it also means that sometimes the switch or the router or the network card might suddenly decide to change paths, and some packets might arrive out of order, and this could cause unusual latency or unexpected changes to latency. And flow control as well can do this, because flow control, if congestion happens, flow control prevents you from losing packets, but it actually also means that things get paused briefly on the network. So that can increase latency and therefore increase jitter. So to reduce jitter, again, one way is getting smarter software on the storage or on the storage devices, like on the SSDs or hard drives. More intelligent or more integrated media management can help. So, for example, some storage controllers will actually understand what the different drives are doing or talk to the drives and, for example, tell the drives, hey, don't do your maintenance now. Wait till I finish this important transaction. Wait till we're not busy, and then you can do your maintenance or your wear leveling or your scrubbing. And another way is don't overload the controllers or don't overload the networks, because overloading the storage controllers or the networks can cause, again, this increase in the randomness or variability of the latency, which shows up as jitter. On the networks, you aim for deterministic latency, where I can guarantee, which basically means I want to guarantee that my network delivers everything with latency below some target level. Sometimes just higher bandwidth helps because it reduces the chance of congestion or packet loss. You can also go to lossless networks or congestion control and some sort of QoS, quality of service. We'll talk more about that in just a second. And those can make latency more consistent. We have to be careful because implemented a certain way, there are cases where if you implement it, you might end up having a more reliable network that actually has higher jitter. So then you have a trade-off between which is worse, losing packets or having higher jitter. So ideally, you aim for a network that does both. It doesn't lose packets and it has low jitter. But it may involve some careful design or some trade-offs or proper implementation of QoS. One example is if you do buffering of the network or the controller is a good way that might reduce jitter, but increase average latency. So it's often used for like media streaming, like video streaming, because if you get to watch your video a half second after it was transmitted, but you don't have any disruptions and everything goes smoothly, you may not care if it's a bit late because it's now smooth and doesn't have this jitter. So buffering is a good solution for something like that. So that, just to summarize, IOPS is a measurement of storage transactions per second. It's important for small I/O workloads or small block workloads. Lower latency is a way to get more IOPS by reducing the average amount of time to finish each transaction. And jitter is the variability in latency. So basically, high jitter is bad because it makes it unpredictable. And people who need jitter to be below a certain amount usually want a deterministic latency, whether it's on the network or in the overall storage ecosystem. So that ends my discuss section on IOPS, latency, and jitter. So I'll hand it back to Fred.
Hey, John, there's a question online. Generally, IOPS numbers like fixed numbers, like 8K or 4K read-write size, but in reality, I/O requests can be any of the mixed size. What do you think about? What's your perspective about that? Yeah,
that's absolutely true, Fred. That most benchmarks use just one side, size, and that's simply because it's easy. It's much easier to do a workload where everything is 4K or everything is 8K or everything is 1K. And some storage devices actually try to, or storage OS try to push all the IOPS to be that size to make it simple. The reality is most workloads could have a mixed sizes. So if you want to have a very realistic workload, especially if you're handling many workloads on one storage device, then yes, you should have mixed assortment of IO sizes. So just like you can mix read and write transactions, you can mix 1K, 4K, 8K, and 16K block sizes. But you really have to look at the workload. Some workloads some databases, for example, might, if you're only running database, might have everything in 4K or everything in 8K blocks.
Okay. One more question here regarding the QDAPs. You mentioned about the QDAPs. Can you say more about like how QDAPs will impact IOPS or latency or jitter?
Sure. So usually a QDAP is basically how many transactions you're lining up for either the controller or the CPU or possibly the network to handle. So it sort of says, when the network is waiting, or the storage controller or the CPU is waiting to do work, I could have four tasks in line, or 8 tasks, or 16 tasks. So if I say my QDAP is 16, I could have 16 things waiting to get done. So a deeper QDAP usually means that as soon as the CPU or the controller is done with one task, it doesn't have to wait. It can immediately start on the next one and then the next one. So it's less likely to be waiting in between, or less likely to have any downtime or dead time while it's waiting for the next task to be assigned. So that is why higher QDAP often means you can get higher IOPS, because the controller you get higher utilization of the CPU. But the higher QDAP, especially if you have multiple jobs going on, different virtual machines or different tasks all be assigned to the same CPU, it could mean that you get higher latency, because the controller or the CPU has to switch back and forth between the different job queues or between the different threads. And so whenever it does the switching, that can produce some latency. So it's not always the case, but that's why I'm saying, generally speaking, higher QDAP could give you higher IOPS, but higher latency all at the same time.
Okay. Thank you, John. I think we can move on to the next topic, QoS. So Alex, now you have the floor.
Thank you. So I wanted to start by defining some QoS terms, and I was seriously tempted but decided not to refer to the Zen and the Art of Motorcycle Maintenance. Now, I have to admit, and from this you should be able to guess my age, I actually read the book when it first came out when I was 17, and it was a great book, and I thoroughly enjoyed it. It was written by a guy called Robert M. Pirsig, and it was about his exploration to try and define value in terms of quality. What does quality mean? And he actually wrote a really interesting line that I like. He conceived the term as undefinable. You can't define the term quality. And the only way to truly experience quality, you have to embrace and apply it as best fit the requirements of the situation. Such an approach would lead to avoidance of a great deal of frustration and dissatisfaction with modern life. Well, quality, I'm afraid, we do need to define it in some way, but sometimes it is unmeasurable, and I'm going to use some fairly loose terms, a bit like Robert M. Pirsig himself. He wasn't particularly accurate on the subject of motorcycles either, as he pointed out. I'm not going to be particularly accurate on trying to measure quality. What I'm going to define quality as is normally meaning fit for purpose, something that is usable in terms that we've defined pretty loosely, and we're defining for ourselves. There's no absolute measure of quality of service. To say I received good quality service is my experience and not necessarily yours. Yours might be completely different. So normally meaning fit for purpose, where somebody's judging the purpose and it's not necessarily the same for everybody. The service itself, on the other hand, is fairly simple. That's the thing we requested, the data that we asked for. And then once we've got the idea of the fact that we've got this soft measure, this fairly woolly measure called quality of service, we can actually talk about some other fairly woolly concepts as well, but they're worth defining. A rate limit or throttling, which is an attempt to provide a capacity limit on quantity delivered per unit time. Now, when we rate limit something, we normally talk about so many X's per second or so many Y's per minute. And that's a real issue when it comes to quality of service management, is defining what is meant by the rate limit. In other words, over what period does it extend? And if I'm rate limiting by the second or by the minute, then I might get completely different results, because I might be suffering from burst. And burst rate is an above average quantity demanded over a brief period. And again, I'm not going to define, frustratingly, above average or brief periods. That is very much in terms of the quality of service that we expect to deliver at the back end. And I'm going to talk about that. Now, we have a proxy for quality of service and its measurement at the back end when I move on to the next slides. So, a lot of soft terms. Quality, you really can't put a number on it. You can define what you mean by quality, and I'll just have to agree with you. Service, fairly straightforward, it's the thing we requested. A rate limit is so many per unit time, and again, I'm not going to define the unit time. And a burst is above average quantities requested in that period, or several periods actually. So the idea here is soft numbers, and then we've got the soft definition of what a noisy neighbour is. And a noisy neighbour, I'm going to define as anyone that you consider to be getting more than their fair share. And what's a fair share? Well, a fair share is when they start restricting my consumption of the same resource. So, you know, I love cakes, and to be quite honest, I'll fight you for the last cake on the plate. And, you know, that's the noisy neighbour thing. It's about who gets what and whether that appears to be fair in terms of the consumer or not. So a lot of soft definitions, but we can use them profitably once we actually have a proxy, and I'll show you what I mean by that in a second. So, is quality of service a measurable characteristic of storage? I believe it is. Yes, we can measure some of these things. What is good quality and bad quality, I leave to you, but we can actually put a number on these things, and then you can use these to decide whether you're actually delivering some measurable characteristic of storage. And we normally use performance measures related to bandwidth, i.e. how wide is the channel we're getting through this, or number of IOPS, for instance, is a surrogate for bandwidth, and latency, how long it takes us to deliver it. And so we're using IOPS as a proxy often for these kind of numbers. And what we're not going to cover here, though, in this narrow definition of quality of service as a characteristic of storage, is end-to-end. We're only looking at the storage element in this. We're not trying to do the entire piece where we go right from the point where the user requests something and the user gets something delivered back at the end. We're also not going to try and define quality in terms of uptime or in recovery time. Those can be elements of quality, but they're not really things that we manage on a short time period. They're much longer time periods that these are measured over. And I'm thinking quality is determined in terms of things that are measured in seconds and minutes, not in hours and days. So meeting quality of service commitments, when you're trying to define some quality of service, you can really say that quality is to do the ability to satisfy the needs of the end user. Now, the end user is typically quite difficult to measure in terms of what we're delivering to him, and also the kind of quality that he might be expecting. So we tend to use other things as a proxy for the end user, and the proxy that we tend to use is the application type, as a proxy. So for instance, we tend to use database access when we're talking to storage. The database is in fact, and the requester of database I/O activity is the proxy for the end user in this case. We're presuming that the end user is being satisfied with the application. And that's where we're not doing the end-to-end piece. I'm only going to talk about the quality of service as we're delivering it to the application. By the way, if you want to ask questions, feel free to do so. So what I'm going to start with is a typical example, and I think we've all experienced this phrase. We all know what a boot storm is. This is a point in a working day, perhaps, where everybody is attempting to do everything simultaneously, and the resources that we have at hand just aren't sufficient to deliver anything. And what starts to happen is the latency goes up, and the number of IOPS we're delivering, or the IOs per second that we're delivering, is dropping down towards zero. And that's classically things like, for instance, a boot storm. Everyone comes in at 8 o'clock on a Monday morning, fires up their laptops. They're in a company of 12,000. That's 12,000 laptops. All of a sudden, attempting to do work across a resource-constrained network onto resource-constrained storage. Obviously, with no QoS at all and no way of managing it or measuring it, the only route to satisfaction there is to actually provide enough resource for any combination of the application workload. That's just horrifically expensive, and to be quite frank, nobody does that at all. So the problem with having no QoS at all and no measure of it, no way to manage it consequently, is that you don't get any protection from the noisy neighbor. You don't get any protection from the application that might suddenly burst into life, consume all the resources, and cause everybody else's applications to slow down. And that overcommit, as I say, of resources is potentially horrendously expensive. The kind of overcommit of resource that you need is the kind of thing that makes cloud storage companies, for instance, very happy, because they are always wanting to sell you that extra burst resource, and it can be horrifically expensive to provide. So we need some way of measuring it and managing it, is what I'm saying. Not having any quality of service is never a good place to be. So we might, for instance, as an example, do some storage tiering. We might decide to classify our storage into gold, silver, and bronze, where gold lives, for example, on flash, silver lives on some kind of fast SAS-based devices, and perhaps the bronze lives on some low, slow-performing SATA device, or even perhaps out in the cloud on a very narrow, restricted bandwidth basis. And we might tier our storage that way. We assign an application to a given tier of storage. One of the problems that we have with tiering is that it's an enormously difficult thing to achieve properly. I mean, unlike any other consumer of resources, I want the best. If flash is available, give me the flash. Why should he have the flash when I can have the flash? If it comes to the division of that cake, I'm wanting more cake than anybody else. I certainly want enough cake to keep me happy. So doing that tends to become a very manual process, and we tend to have problems, for instance, with, again, noisy neighbors who steal performance, and again, with actually having to manually move and migrate data from one tier of storage to another. We also have the problem of, for instance, to give you classic examples, in industries that have periodic applications, end of month, for instance, you may require to have all your billing files on flash for the end of the month just to get them through, but you really don't want them there during the other 29, 28 days of the year, and you want them on slower storage. So the stuff needs actually moved, and it needs moved in advance, because there's no point having it on a bronze or a silver tier, and then having it move as you're actually running the application. That's dragging the data through these storage layers, and by the time it's processed, it's too late. You've moved it up to the flash level, but you finished processing it. So it's a very difficult process to manage, and manual movement of data is very expensive. Noisy neighbors still steal performance, and the workload performance, a lot of workloads can be affected by the fact that the back end of the storage systems are spending a lot of time moving data around, not processing it, not providing it to applications, but simply shifting it from one tier to another. So although storage tiering does have some benefits, it's a remarkably difficult way of managing. And in fact, one of the things that I would suggest, it's a bit like trying to cut a block of wood with an axe. Hitting a mark very accurately with an axe is not particularly easy. So again, storage tiering is like that. Deciding what should be in flash and your gold level is often very difficult to do accurately with any sense and any size that's going to give you any benefits in terms of cost. The next one down you can look at is to prioritize the application. You do class of service. And this is quite common. You rank applications and you say, this is my mission critical application. This one is non-stop. It's got to have high quality of service. It's got to have low latency. You know, it's going to demand a certain number of IOPS. And then I have other applications that are moderate or perhaps low in terms of the requirement. But that again is a fairly difficult process to undertake. There are many different types of applications that you need to consider. You need to consider your entire application estate very often to be able to identify them as mission critical, moderate or low. Again, the performance is based on arbitrary levels. What's meant by mission critical to me might be different from mission critical to you, but I've only got one mechanism by which to differentiate them, and that's the label I put on them. And noisy neighbors get worse, much worse, if they're prioritized as mission critical. So if something that does burst the I/O and turns up at Monday morning at 9 o'clock and consumes loads of resource, but it's classified as mission critical, then you really haven't helped yourself at all, and you're still back to having the problem of not being able to prioritize applications accurately and effectively and still having to overcommit resource. So that's two techniques. Excuse me. There's a third technique where we could actually I/O rate limit by application. We could actually do that thing about rate capping. We could say these applications are only allowed to take so much I/O, so I can take the noisy neighbors and I can limit them in terms of the amount of performance or latency that they get from the system. And in that way, cap them and try and prevent them from being disruptive to other workloads. The problem with that is there's no minimum performance guarantee. So I can actually sit around waiting for something to happen for quite a long time, because again, I'm still resource constrained. I'm just slicing their resources up differently. Excuse me a second. Dear me, I beg your pardon, I've got a bit of a cough. And this is actually quite difficult to do, rate limiting, because it needs to be done at the application layer. And if you think about it, storage, to a large degree, doesn't have a very good sense of what represents an application. What it's seeing is a stream of I/O. And it can rarely tell. If you're on a, your block-based SAN system, you can rarely tell what application is actually sending you the I/O. Perhaps you're splitting things out by volume, so applications by volume, you've got some idea of what's going on. But the I/O that's coming through to a SAN looks remarkably uniform. We don't really know what systems it's coming from. So it can be relatively difficult to do unless you've got sufficient measurement or smarts in the application. So a fourth technique, and one that I think is beginning to make more sense as we have more measurement points and more ways of managing our storage systems, is to do minimum maximums and bursts and put things in a box. In other words, what we're doing is we're saying for this particular application, we're going to try and put you in a box. We're going to give you a minimum amount of service. So if you ask for this, you'll get it. We're going to give you a maximum amount of service. If you ask for more than this, you're not going to get it. And what we're going to try and do is control the amount of bursting that you do as well. So you're allowed to take 50% more for, let's say, a minute. But after that, we're going to start rate capping you back down again. And the idea is to put, if you like, if you look at the diagram, I'm sorry it's so small in what you're saying. If you look at the diagram, basically what you've got is a cube, some metrics that we're using, and a ball in the middle. The application is bouncing around inside the cube. And what we're trying to do is constrain that ball inside that cube. And there will be many cubes, one for each set of applications that we have, where we're trying to put these applications and constrain them. So it's if you like, a refinement of the other techniques in that we've now got more dimensions over which we're trying to manage quality of service. So other QoS techniques we can use, we can add further dimensions. We can add more dimensions to this idea of constraining our application, which is a proxy, if you remember, for the end user, in terms of the resources that it's consuming, try to constrain it inside this box, and then having boxes that we can deliver the resources for. So we've got caching. Again, very similar considerations for storage tiering. A lot of people believe that caching is a wonderful thing, and it is for certain types of workload. Funnily enough, it's not the kind of workload that most people think of. It's really good for write workloads, but it's not particularly great for read workloads. For write, it smooths out the write operations so that we can tolerate, if you like, a much higher rate to cache, and then we can clear out our cache at our leisure. As long as we don't overrun the cache, we can make the writes look like they're going much faster. But reads, unfortunately, read caching is a fairly sophisticated thing to do, and there are very few ways of predicting what people are going to read next. Perhaps sequential I/O is one of the very few of them. So that's a problem. Also, the storage is normally unaware of what the application of the client is doing in terms of caching, and the two can disturb each other. So the application of the client can actually cache data and then talk to the storage system, provide a completely different I/O profile from what is being asked for by the application because it's caching itself. So depending on where you cache and how you cache, you can provide some benefits and provide some quality of service, but it's much more difficult to handle. And it requires a lot of smarts in the storage system as well. Outside the storage system, because remember, storage is always talking externally to other pieces of technology, particularly in this case, networking. You can use network bandwidth management and traffic shaping, and these kind of tools and techniques are regularly used in the network world. Exactly the same criteria. A network is a finite resource. You can deliver so many bytes per second over a network. And again, you can shape the traffic. You can rate limit the amount of resource that you give to a single application. And you can do the same for storage. You can prioritize your storage across the parts of the network that are not solely for the for the storage system's use. And whole end-to-end network management is difficult for the storage system to provide. So this again requires a more holistic approach, and you need to use not just storage tools, but also network management tools to be able to provide an overview of what's going on in terms of storage and network. Storage alone can't provide you with any half-decent network management. Again, compression, you can use compression. And compression allows you to, as a client or an application or as a storage system, to compress the data. If you're compressing at the storage end, that's fantastic. You still got the network load though, and compressing at the storage end rarely provides you with a better quality of service. Best to start by compressing at the application or the client end. There are other things as well that may help in terms of processing and providing a better quality of service. For instance, deduplication. Deduplicating data can often be a benefit. Not only does it reduce the amount of capacity resources that we require, but if there are many people using the same piece of data, then having deduplicated and only having to do the one I/O to satisfy many requests might be a way of providing, again, improved quality of service. So in summary, quality is a really difficult thing to measure. It's very much an individualistic approach by what you mean by quality. Service is the easy bit to identify. It's the data we're receiving and storing and then delivering back to the end user. And we tend to use applications as a proxy for the end user in terms of performance. And then there are the mechanisms that we can use are things like storage tiering, or we can use rate limiting techniques and give minimum and maximum I/O, or we can use a combination of these techniques and provide, if you like, a multi-dimensional cube or N cube where we're trying to constrain the application in terms of its resource consumptions inside this cube, so we can have multiple of these that allow multiple applications to all benefit from the quality of service that we would like to deliver to them. So I'm just going to see very quick, see if there's any questions. Any research being done on using storage analytics along with AI to assist QoS? The AI we currently have with QoS, I'm afraid, is wetware, brain power. There are a lot of analytics though. There are an increasing number of analytics tools in the storage and networking area that allow you to profile traffic and to make some predictions as to future and present resource consumption, how it might best be balanced. And measurements to calculate IOPS megabyte per second in the capable tier storage. Yes. So the question here is about making sure that you've got the right bandwidth to a given tier, and that's also important. That's one of the resource criteria that you have to take into consideration. Resources, when consumed by applications, tend to be measured in terms of capacity and IOPS, and there's also a quality dimension to capacity. So if you have a huge amount of capacity required, but a very low IOPS rate, then that's one aspect that we can meet perhaps by having a particular type of storage profile. And then we might have the other, which is a very small amount of storage, classical things like databases, but a very large amount of I/O, because they're doing a lot of updating of databases or reading or writing from databases. And again, that's got a different type of profile. So yes, capacity and the bandwidth to that capacity are criteria that we use when putting together the resources and building a picture up of how we deliver quality of service across multiple applications. So that's me. That's the summary of QoS, what QoS means, and it's a fairly woolly subject. However, Zen and the Art of Motorcycle Maintenance, I can recommend as a book.
Okay, thank you, Alex. Before we conclude this presentation, I want to introduce the next one of the series of everything you wanted to know about storage but were too proud to ask. We'll have a Vermilion session, What If Programming and Networking Had a Baby, arranged on July 6th. We'll talk about storage APIs and POSIX, block file and object storage, byte addressable and logic block addressing, log structure and journaling systems, and all interesting topics. So you can register here on the link. And also, if you have so if you're interested in the topics that we presented in the past, you can find all recorded webcasts on the links here. And also, you can follow us at SNIA ESF for all the announcements and new topics. And if you are interested in the storage performance benchmarking, we have a on-demand session here. And then I think that's the end of the presentation. And you can find the material on the website. The PDF version posted on the website already. And we do have more questions online that we don't have time to answer. And you can find a full Q&A blog on our website. We'll post it on our website after the session. And please follow us on Twitter. And if you need additional help, and you can also download the SNIA dictionaries on the link here. And from here, we will conclude the session. Thank you. Thank you for joining us, and look forward to meeting with you for the next one. Thank you. Bye.